So we're going to do the integral test, and I am going to skip by the prove it's positive and prove that it's decreasing part, right, for speed. But you would be expected to do those at least in the tests, right? You may not do them in your homework, I can understand that, but at least in the test, you must make sure you do that. So we're going to look at starting a lot of questions, because for time purposes, I can't do them all the way to the end, because, you know, that way I'll be able to do more different kinds of questions. So this is my version of question 9. I want to integrate this guy, and it's going to be from 1 to t, that's 1 to infinity. So if I put that line in, it saves me having to write the 1 to infinity thing. And now I've got the square of x plus 2 over x squared. So what I want to focus on for the next few questions is the integration techniques that you need to use rather than the other stuff that came before. Now, if you try and integrate that the way it stands, would you agree that you're going to be in real trouble really quickly, because it ain't going to integrate? So we have to figure some way of dealing with it. So it's going to be this fella. Oh, well, maybe you could tell me, what would be your strategy for integrating this ugly fraction? How would you have approached it? Because it may not be the way I'm going to do it, but that's fine as long as it works.
I broke it up into
That's
two different
good.
fractions, or at least two different sums is what the video showed it to do.
Right.
Showed them as two different P series.
Okay.
Sums.
Ah. So you decided, if I'm picking up right, to split it up like that. And then this guy, eventually, with a little bit of algebra, became that. And this guy became that. And so you're actually doing this question as a P-series question, right? Now, isn't the p-value 3/2, so it converges? The p-value is 2, so it converges. The whole thing converges. That is totally cool. I like it. Keep doing it. But since I've set up the integral, not everyone sees the same, you know, the same question the same way. So let's look at just a different approach. My approach, by the way, is going to be a lot longer, so I like yours better. Now, algebraically, how do you deal with that integral? Any takers? Okay. You could call it x to the half plus 2 and multiply it by x to the negative 2, which means it would then turn into x to the negative 3/2 plus 2x to negative 2. And at that point, would you agree it's just a very ugly power rule? And then you'd get the answer. Oh, I guess I should write down the next cell.
I have a question on that one. Is that one of the ones that you have to tell what it converges to?
No. In these questions, you only need to decide convergent or divergent, nothing else. So this fella, he becomes, I'm even abbreviating myself even more. He becomes that guy, right? The other stuff. Let's just focus on the integration part. That's really all I want. So I'm probably not even going to put those in next. Do you know that that guy is a standard integral? What you might or might not know is what he's equal to. Okay. So when you are doing that fella, this is what the antiderivative is. So you would evaluate it at x equals 1. Don't need that anymore. At x equals t, and then you put infinity in. By the way, it would converge. Question 11. That's the guy. That means we have to integrate that guy. Okay, what technique will you use to integrate 1 over x log x? Silence is not good. Calc 2, my Calc 2 right now, by sheer coincidence, are doing exactly this kind of question. How do you integrate?
Substitution.
Correct. What is the U sub that you would need to make this thing work?
I would use the natural log of x.
Right. And off you go. And if you use the natural log of x, I believe that thing diverges. Don't quote me on that. If you were doing question 12, you would eventually have to integrate this guy. What technique would you use to integrate this guy? Come on, what kind of technique would you use to integrate this guy?
Wouldn't you do the same? Would you do a U sub?
Yeah. Just because it's a different question doesn't mean we can't use the same technique. Let's do the U sub on this one, because this one is not easy.
Could
Right.
you also take the natural log of x out of the integral and then do a p series of 1 over x squared?
I wish you could do that, but the reason you can't is because there's got an x in it. So you can pull things out as long as they don't have x's. If they have an x, they have to stay put. It would be so much nicer if you could. And you might end up wrongly getting the correct answer. In other words, you do that and the answer is, oh, it converges, and that does happen to be the correct answer. This one does converge, but not for the reason that you did, right? You know, you can get the right answer by doing something wrong.
That makes sense.
Right. So if you differentiate this fella, well, we've done that, you get that. If you do what I call the crossover, you get that, right? Now, over here, what have we got? Well, we've got the natural log of x, which is u. We have an x squared, and the dx gets an x du. And this fella becomes u over x du, which is normally very worrying when you do u subs, but not all the time. If u is the natural log of x, isn't e to the u also x? You agree? Which means that this fella becomes u over e to the u du, which then becomes u e to the negative u du. We have changed an ugly fraction into this guy. This guy, of course, needs another technique done to it. So this is like the ultimate ugly integral. What technique do you use to integrate this fella?
Is it integration by parts?
It is. Would you agree that that is a very ugly question? For a very simple answer, converges or diverges? And I'm pretty sure that one converges. Does anybody know how I can look at these guys and know they converge or diverge?
Couldn't you look at the ratio, or you could go ahead?
Oh,
Yep.
I just kind of had a question. Once you get to that point, if you have the u over e to the u, could you use something like a p series to kind of just look at it and say, oh yeah, converges?
P series don't work with e to the u. They only work with n squareds and n cubes. They don't work with EUs. You really do want to use P series, don't you, Molly? I don't blame you. I would want to use a P series as well. The reason I know that these work is that I look at a function and I try and look at what it behaves like, which is kind of connected to Molly's idea. Do you know that guy there will probably behave like a 1 over n squared? And I know that converges. But that's not a proof. That's just, I know 99 times out of 100 what the answer is. But you know, 1 times out of 100, that trick doesn't work. And that's why I need to prove it. Because you know, the one time you don't do it is the one time you should have done it the right way. Right? And you don't want bridges falling down. Right. Okay, question 13. You're going to be integrating that guy. Okay, what technique will you use to integrate that guy?
Integration by parts.
Correct. Question 14, you're going to end up integrating this guy. Looks very similar, but it's a different method. What method will you use in 14?
U sub.
Yeah. And who will the U sub be?
Negative x squared.
Yep, or x squared, both work. This is sneaky. It's a U sub. But it's not x to the 20 plus 1. Do you know what the U sub will be? It's a really sneaky one.
X to the 10th.
Yeah. Can you trust me that it turns into I don't know, a 1 over u squared plus 1, I'm pretty sure, with, I don't know what fraction of it. It's either going to be a 10th of that or 10 of them, right? Can you see an inverse tan, and off you go from there. Oh, okay. So far, so good. Now, that was a crash course on what algebra technique you will be using, right, to integrate something. And a lot of those questions are going to be quite long because of that. So now we are going to do some questions to do with accuracy, errors, and estimates. Let's take, for example, this fella. Right. I know that that guy converges. Isn't he a P series? P equals 2 converges. That was the easy bit. What I'd like to know is, what does it add up to? I'd like to do at least an estimate of what that series adds up to. Now, if I do the integral test on it, the integral test tells me it converges, but the number it tells me it converges to isn't really the number that this adds up to, right? So if I find the integral of 1 over x squared from 1 to infinity, I may get the answer 5. That doesn't mean this adds up to 5. It just means that it converges. So we need a different technique for doing that. And here is the ugly formula for what that is. Let's say that this adds up to a number, and I'm going to call the number capital S. The integral test has a formula that allows us to put a boundary on S, right? It's between this guy and that guy. And it's the partial sum at n plus the integral from n to infinity of this guy. And on the other side, it's the partial sum Sn plus the integral from n plus 1 to infinity of, whoops, that guy. Now, that, I'm going to have to write that again. It's just too much of a mess. I never planned. When you want to get an estimate of the correct answer, right? What you can do instead is you can find these two things, the one on the left and the one on the right, and that means that the answer is in the middle. So what are the errors involved in that? Well, if you know the boundaries, can't you say the difference between the two boundaries divided by 2 is my error, right? Plus or minus 0.04. So we have to decide which partial sum to use, right? Because n is the partial sum. Would it make sense that if I use the first 10 terms, I'm going to get a more accurate answer than if I use the first 4 terms? Okay. So let's say that this question asks us for the first 4. So the first thing I do is I just find out what S of 4 is. So S of 4 is, I can do it in my head, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, right? And then I go to my calculator and I find out what 1 plus a quarter plus a 9th plus a 16th is. And typically you would probably call that a fraction, but I'm not going to. I'm just going to write it down as a decimal, because whenever you do errors, you know, things are going to get rounded off anyway, so you might as well just bite the bullet and have everybody as a decimal. So my estimate for this partial sum is 1.4236111, right? That's what my estimate is. What I'd like to know is, how good an estimate is that? That's what this will tell me, right? I mean, is it that guy plus or minus 0.1, or is it that guy plus or minus 0.001? You see, that makes a difference, right? How good is my estimate? And that's where the accuracy and errors comes in. So what you need to do is you need to calculate these fellas. So I'm going to find the integral from 4 to infinity of 1 over x squared. And I'm also going to find n plus 1, 5 to infinity over 1 plus x squared. Okay. So far, so good. Now, I'm going to get decimals for each one of these guys as well. And I'm going to cheat. Well, let's say cheat's a bad word. Let's say I am going to be efficient in my calculations. Now, couldn't I go through the usual, turn it into x to minus 2, power rule, plug in the thing, make the thing go infinity, 5 minutes later get the answer, 5 minutes later get the answer. But since this is numerical and we're doing the engineer get out, doesn't the engineer just, aren't you happy with good enough? You don't need exactly the answer, good enough will do. So this is my cheat. I'm going to go in here and I'm going to do 1 divided by x squared. And I'm going to go to my window and I'm going to start at, yeah, 1's a good number to start at. Yeah. And I'm going to go all the way to, how about 100? Would you agree that's not infinity, but it's big enough, right? It'll do. And then I'm going to go zoom 0 so I can get a quick sketch of it. Have I broke this thing? I broke it. I broke it. Okay. You're not my friend. Stop doing that. Okay, I'm going to cheat a little bit differently then. Evidently, it has a problem with 1 over 100 squared. Why it would have a problem with 1 over 100 squared, who knows? Can I do 20 then? I shouldn't break it on 20. Let's do a zoom 0 this time. Yeah, there we go. Okay, would you agree by the time it gets to about wherever my finger is, isn't the answer pretty close to 0? So it shouldn't make much difference. Now I'm going to go second calc, number 7. I'm going to do 4 to infinity. So that's going to be 4 to 20. And the answer I get is 0.2. And then I'm going to go second calc, number 7, and I'm going to do 5 to infinity. Only it's going to be 5 to 20. And the answer I get is 0.15. So according to this expression, the real answer is somewhere between S of n, which is this number here, 1.4236111, plus that guy, and S of n plus that guy. And then I'm going to use some common sense. If that's my error, would you agree that this is far too accurate to be even reasonable? So I'm going to call this guy 1.42. And now I have 1.44 to 1.435. Do you get at least a good picture of what that guy adds up to? Doesn't he add up to some number in the range 1.435 to about 1.44? Do you see I've got some tolerance on it? Don't know exactly the answer, but isn't it living somewhere in there? Can you see how long these questions are? Even when I did a little bit of cheating, shortcut, whatever you want to do it, they still involve a fair amount of detail. What do you think would happen if I decided, instead of using S4, that I said S10? What would you think would happen to the boundaries?
The boundary would get smaller.
Yeah, with a bit of luck, it might end up being a lot smaller. I'm going to pretend I know the answer, which I don't. You might end up with an answer that looks like that. Do you see that if you choose S4, the answer to the, what's the thing going to add up to is not going to be as accurate as if you use the first 10, right? S10. If I used S a million, I'm not doing it because I broke it on 100. Can you imagine what it'd be like on a million? But couldn't you plug it into a computer? Couldn't S a million basically tell you the answer? So that's our strategy. We might not know exactly what this adds up to. We know it converges, but we have this weird formula that basically says you take whatever accuracy, the partial sum you've got, and if you add this integral and this one, you've got your boundaries. And that's basically it. So next question is 17. And question 17 has a guy that looks like this. And we have to estimate this guy correct to 5 decimal places. Since they're already telling me it's to estimate the answer, can we just assume that it converges? We don't need to prove it because the way the question is phrased, it's pretty obvious that it is. But we have to estimate this guy to 5 decimal places. And the only formula that I've got to work with is the ugly one that looks like this. Do you notice that I've turned this guy into that guy just because to me it looks prettier, right? I've only got this guy to work with. Now, if you want the answer to be correct to 5 decimal places, then don't you want this fella to be 0.00005 decimal places, 0, 5 nothings, and a 5? Don't you want the 6th decimal place to be a 5? That way, when you round it off, it's going to work, right? So basically, our problem is, what does n have to be equal to for this integral to be that small? Right? So what value does n need to be to make this integral that small? That's our problem. How do you integrate 2x plus 1 to the power of 9? Well, let's look at it. It's going to be an integral from n to t. The limit as t tends to infinity. 2x plus 1 to the negative 9 dx. That's the guy that we're going to be integrating. How do you integrate that ugly power? Help to u sub. Who would the u sub be?
2x plus 1.
Great. Differentiate with respect to x. Multiply both sides by dx. I call that crossover. Isolate the dx. So this fella now becomes u to the power of negative 9, 1 over 2 du. So basically, I don't know if I need this line, I'm putting it in there anyway. Right, that's the guy that it ends up becoming. Add 1 to the power and divide by the new power. It becomes this guy. Return them back to the original. Evaluate it at x equals n to x equals t. Rewrite it as this guy. Substitute in x equals t and x equals n. And you get negative 1 over 16, 2t plus 1 to the 8. Take away a negative is like adding it. 16 to n plus 1 to the 8. If you plug infinity in here, would you agree that disappears to 0? So the answer is this fella. And we want this fella to be approximately equal to that guy. So just when you thought you'd finished, do you see you've got more work to do? What we're going to do is solve for n. Right? We're going to find out what n has to be to get an answer that's about this size. And once we do that, we have answered the question about how big n has to be. So any suggestions how to start thinking about solving that question? I use a technique that's called, as long as you do it to both sides, it's okay rule. So what would you do first to solve this ugly equation?
Multiply by 16.
I would. And so you would have this fella. 16 times 0.12345 zeros and a 5 ends up being 0.12348. This question has just got tons of puzzles to it, and I'm only doing half of it. Once I finish this bit, the rest is yours. What do I do next? Oh, I got you puzzled. How about 2, 8 plus 1 is 1 over that guy. Which in turn is 1 divided by 0.00008. So I'm now looking at 2n plus 1 to the 8th is 12,500. Okay, we're almost at the end. We've almost solved it. What do I do next?
Take the 8th root of the 12,500.
Okay, so to the power of brackets 1/8. And that is about, what, 3.25? What do I do now?
Subtract 1 from both sides, then divide by 2.
Wow. You only need 1 and a bit terms, right? 1 and a bit terms. To err on the side of safety, wouldn't you choose 2 terms? Agreed? Now, what do you do to finish? Just find S2. S2 will be good to 6 decimal places. Do you see that that series converges to its answer so quickly that only the first couple of numbers in the series even matters? Can you imagine what the third number would look like? Can you imagine it would be 0.12 zeros and a 1? Can you see why it doesn't matter after the first couple of terms? All the numbers are contained inside it. So that actually finished a lot easier than I thought. Because all you're going to do is plug 1 and 2 into that. So what's that going to be? 2 times 1 plus 1 to the power of -9 plus 2 times 2 plus 1 to the power of -9, which I would turn into 1 over 3 to the 9 plus 1 over 5 to the 9. That's the only 2 guys you need to add to find what this converges to 5 decimal places, which is actually phenomenally easy. I wasn't expecting it to be such a nice number. I was expecting, you know, like, oh, you'll need 10 terms. That's why I said, well, you're going to finish it off yourself later. But actually, it's only 2 terms, isn't that a lot less work? And I'll keep that for a second. It wouldn't surprise me, and I strongly suggest that you go back and watch the end of this video a couple of times so you can keep track of all the things that were going on, because there's a lot going on. Right, let's jump over and show you what that homework looks like. The guy I just did was question 17, at least my version of it. You see it that? In this one, you watch a video and it basically takes you through what I just did. And in question 19, you watch another video and it tells you about that. So the last 3 questions involve you pretty much watching videos and it tells you what to do. So you can imagine that if it's that difficult, they kind of had to do it. Yeah, I did like walk you through the steps. And that is the end of the integral test. Questions? Apart from how on earth do you do it? that one doesn't count. So I'm now going to give you an intro to the next section, which is 11.4. And the 11.4 is going to be the direct comparison and the limit comparison test. And this fella is a lot easier. So guess what? I think would you agree the integral test has got a lot of stuff going on, a lot of things you can go astray on? You're going to find that these tests, the direct comparison test and the limit comparison test, are in comparison going to be relatively easy. Now, let's start with some people that we know the answers to. Because in these questions, you are going to assume that these are true. Do you recognize a P series? And do you recognize a geometric series? Right? P series, geometric series. So far, so good. Now, in a P series, can't you just say P equals 3, that's greater than 1, it converges. Right? That's a very shortcut, basic. Molly, your favorite series, right? P series. This is a geometric series. What's the letter and the number that you use to test geometric series?
R and A.
Right. And for convergence, don't you only care about the R? And these questions, we're only interested in convergence, so we're only interested in the R. So in this case, R is a half. And as long as the absolute value of it is less than 1, which it is in this case, it converges. Now, don't we also know when P series diverge? And don't we also know when geometric series diverges, right? So I haven't put them in, but you can do that. We are going to use those two guys as our comparisons. In other words, I'm going to have a series and I'm wondering if it converges or not. And so what I do is I take that series and I find out who his comparison is. Who does he behave like? And if I can pick that guy correctly, then if the guy I compare him against converges, so does my guy converge. And if the one I compare him against diverges, so does mine. So it basically, you take an ugly series and you look at a simpler version of it and test that. Okay, so give you an example of how that might work. Take that series. Now I could split that guy into two pieces and do two P series on it, but let's do a comparison test on it. So start with my little guy over here. Break it down into the basic steps. So step 1, find a guy, the comparison guy, sigma BN. When I look at this series, what I try and think of is what it would look like if I simplified it. I have a nickname for it. I call it surgery. So I take this guy and I use those funny little OC, looks like an equals. Actually, it just means approximately. Would you agree that that guy approximately behaves like that guy? Would that seem reasonable? I mean, if n is a billion, would you agree 1 billion and 1 over 1 billion cubed and 1 billion over 1 billion cubed? They're not that different, right? They're very similar. They behave the same. And isn't that guy 1 over n squared. You with me so far? Now, what do you know about the comparison test? What do you know about that guy? Who is he? And does he converge? Come on, don't scare me.
It's
One
just
of-
a P
Series, right?
series, right?
Yeah, it's a P series. It converges. Agreed? Now, what some people do, unfortunately, is they think, I'm finished. That guy behaves like that guy, he converges, right? The answer is he does converge, but we got to prove it. So what does the limit comparison test say? It says the following. You need to find the limit as n tends to infinity of an over bn. In this case, the limit as n tends to infinity of the original series divided by its comparison series. And what the limit comparison test says is that if this limit is a number, and we don't care if the number is 1, 41, or a half, it just must be a number, then we can make the assumption that the series converges. If this fraction ends up being 0 or infinity, what that has done is it's proven that we chose a bad comparison, because sometimes you choose a comparison that isn't actually valid, right? So it's like a check to make sure that you haven't screwed up on your comparison, right? Because I could compare that guy to somebody he's nothing like, really, and say, hey, the guy I compared them against converges, so that proves my guy converges, right? So we can't really do that unless we kind of double check it. So okay, you want to think of this as our double check that we've proved, you know, that we've made a good comparison. Now, one of the awkward things about these questions is that you're going to deal with fractions. Would you agree? Fraction over a fraction is not very elegant. So I'm going to turn it into something that's a little bit easier to deal with. Instead of a fraction over a fraction, can't I turn the second one upside down and mathematically it's the same thing? Agreed? Now, if I do a little bit more work, can't that partially cancel? And now I am left with n plus 1 over n. So far, so good? Right, tell me, I know the answer is 1, right, which is good, because I want a number. Tell me how I can prove it's 1, because you got to prove it to me.
L'Hopital's.
Yeah, why not? L'Hopital, 1 over 1 is 1. So, according to the limit comparison test, if the limit of the original fella divided by its comparison fella is a number, then they behave the same way. So in this case, this converges. I have now proved that that converges. Does the logic of that kind of make sense? That if your series behaves like another guy and the other guy converges, so should your guy. Yes, maybe. How about this fella then? Oh. N squared over e to the n. Do you think he's going to converge or not? What's your gut feeling? A series either converges or diverges. It's only get two choices. What do you think? Don't know. Okay.
I was gonna say diverges, but
It might be. Now, I need a comparison guy, right? That's my A in. I need to have a B in. I'm picking that guy. Okay. Why do you think I chose that guy as the comparison fella? If I write him like this guy, do you see a geometric series? Agreed? Do you see a geometric series there? What's the R value in this geometric series?
1/e.
So does this converge? Is 1/e less than 1?
Yeah.
Yeah. So I know that it converges. So if this is a good comparison, shouldn't the limit comparison test, shouldn't this be a number? Well, let's see what we get. It's going to be the limit as n tends to infinity of an over bn. So it's going to be the limit as n tends to infinity of n squared over e to the n divided by e to the n. It's the limit as n tends to infinity, and it's a limit as n tends to infinity of n squared. The answer is infinity. Do you see that I chose a bad comparison? I would not have known that that was a bad comparison. If I had thought that that behaves pretty much like this guy, wouldn't I then have come up with a conclusion that this fella converges? And that isn't necessarily so. So do you see why you need this fella? Because this fella will keep you honest. If this is a number, as long as it's not 0 or infinity, if this is a number, then that conclusion will be true. If this is infinity or 0, you've chosen a bad comparison, in which case you would have to figure another comparison to do. Actually, that question would probably have to have been done with the integral test. And I would have written it as n squared e to the negative n, and wouldn't have done integration by parts. If you're just wondering how I would have solved that question.